All right, here we go, continuing on with acids and bases. 4C1, I can identify a substance as an acid or base by its properties, including pH, reactivity, dissociation in water, taste, feel, and chemical formula.
But first, what exactly are acids and bases? Well, acids, sour. So sour. That's the first thing that we learned about acids, actually, and that's why acid, actually means sour in Greek or Latin. And acids are excellent at dissolving stuff. They kill things and melt your face. What about bases? You might have some idea of what a base is. Bitter tasting, slippery, like soap. Soap is, in fact, a base. And bases, like acids, are totally dangerous and can melt off your face. They're also like the anti-acid, basically. In fact, they're in antacids. If you mix acids and bases together, they neutralize each other.
All right, let's look at some characteristics, some differences between acids and bases. If you're an acid, your pH, and we've already talked about pH, is below 7. Below 7. If you're a base, the pH is above 7. I would write this down. I would record this somewhere. An acid gives a hydrogen ion. We'll talk more about what H pluses are. And that's a typo. Yes, we got some typos here. All right, so pH above 7. The hydrogen, an acid will give a hydrogen plus. A base will absorb a hydrogen plus. There is a indicator. Turns red. In an acid. And the litmus indicator, it's a chemical that indicates, changes color in acids and bases, turns blue for litmus. Tastes sour for an acid, tastes bitter for a base. Slippery, feels slick. Reacts with metals to form hydrogen gas. Does not react with metals. Those are all characteristics you might see in one way or another on the EOC, which is a week from Thursday.
What?
EOC is a week from Thursday. This, for some of you, will be your defining moment. You can still actually salvage this 9 weeks, well, actually this whole year, because it is 20% of your grade. 1/5 of your grade. All right, we good?
No, sorry.
Go into the lab, the door between the two halves of the lab, there's a box of Band-Aids there. Folks, also remember we have a lab on Wednesday, and a lab that will include 6 molar hydrochloric acid, which you ought to know that 6 molar is actually pretty concentrated. So make sure that you wear appropriate clothing.
Okay.
We good, Ben?
Yes. Thank you.
I can distinguish between Arrhenius and Bronsted-Lowry definitions of acids and bases. I can identify common examples of acids and bases. If given an acid-base reaction, I can identify Bronsted-Lowry acid-base, conjugate acid-base, particles. We'll see. All that will make sense to you here in a little while. Who first defined acids and bases? Savante Arrhenius. Savante Arrhenius. What was his definition? Okay, back a long time ago, you could actually look into a room through its keyhole. That's when the whole concept of a peeping Tom came into being. So you could kind of see what was going on through the keyhole. If all the acids and bases were in a room, Savante did not have the guts to go into the room. He simply peered in through the keyhole. What's the problem to looking inside a room and trying to identify what's in the room by using the keyhole? What? It is creepy, that's right.
You got a small view.
You only have a very narrow view of what acids and bases were. So he had a very narrow view. He said that an acid is anything that gave hydrogen ions, and a base is anything that gave hydroxide ions. He was, for the most part, correct when it came to acids. For bases, he was phenomenally off base. No pun intended. Actually, just a few bases have hydroxide in them. Most bases do not have hydroxide. They do not. They do not. Two examples of common acids and bases. Acids, ascorbic acid, vitamin C. That's why those vitamin C tablets taste so sour. Sometimes you'll get them as gummies, in which case they've added some sugar to it. Acetic acid tastes sour, vinegar. Hydrochloric acid, if you ever had heartburn and some gastric juices went up your throat and into your mouth, that's muriatic acid. That's hydrochloric acid. That's in your stomach. Bases. Sodium hydroxide is what we call lye soap.
All you use that to get rid of lice.
I've never heard that, but I wouldn't be surprised because it'll kill virtually everything. I mean, sodium hydroxide is so basic, it'll burn off the top layer of your skin. People who use sodium hydroxide as a soap can't shower every day because it dries out their skin too much. Fortunately for us, we no longer use lye soap. We use chemicals that are a whole lot more gentle on the skin. But there's some people that are actually allergic to those chemicals and they're okay with lye. That's pretty crazy. If you've ever been to Dollywood, they'll make lye soap there for you. You can see them making it. It's a very toxic environment around where they make it, so they have to make it outside. I mean, we could do it in the lab. It's just real stinky and smelly and involves animal fat and sodium hydroxide, and, well, it's too dangerous for me to do at the high school level. Calcium carbonate is limestone. Rocky Top is mostly limestone. They should change the words to Rocky Top. Good old limestone, limestone, Tennessee, limestone, Tennessee. Yeah, it's just, yeah, it doesn't sound the same, but it's probably more accurate. Sodium bicarbonate. I have very bad feelings about sodium bicarbonate because every time I had heartburn. I had heartburn as a kid a lot. I guess it's because of the foods I ate. So I would complain, and my grandmother would reach for the baking soda, sodium bicarbonate, and give me this huge spoonful of this white powder, and it tasted really bitter, and I can still taste it. But within seconds, I'd be burping up a storm. Within minutes, I'd be feeling better because the sodium bicarbonate was neutralizing all the excessive acid, the excess acid that was in my stomach. What exactly happens when acid dissolves in water? It breaks down into ions. it breaks down into ions. And the key thing is this H+. That's what makes it an acid. If it gives out that H+, that's an acid. Now, let's think about what hydrogen is. Hydrogen is one proton surrounded by one electron. Just a proton and an electron. If it loses that electron, which it will as an acid, that's what it does, it loses an electron, leaves it behind, then what is left? So an H+ is the same thing as a proton. Okay, so whenever you see a proton, that's basically the stuff that hydrogens give. Now, this proton won't stay around for very long. It will actually be picked up by water. Notice that water has two pairs of electrons that it's not sharing with anybody. Hydrogen comes around and it's boo-hooing because it thought that it was going to be happy giving its electron away, but now it's not happy anymore. It misses the electrons, the two electrons it used to have. So it's boo-hooing and crying and just carrying on, and the water goes, "Hey, buddy, come over here." What? I lost my electrons. Well, you know, I have 2 electrons here. I'm not sharing with anybody. Would you like to share with me? And the hydrogen goes, yes, please, thank you. So it comes over and it shares. So that now you have what is called hydronium ion. It's H3O positive. So in other words, H3O positive and H+ is the same thing. It's H+ plus water. We don't actually think that a proton just hangs around and exists without it binding with water. H2SO4 is sulfuric acid, most useful of all acids, and you see there that it will give off an H+. Did you notice what's happening to the charges? If you have a plus here, you must have minus. So what problems did we encounter with the Arrhenius definition? Not all acids gave H+. Now I have to admit probably the vast majority of them did. So by and large he was correct when it came to H+, to acids. But he was nowhere close with bases. Not all bases have an hydroxide to give. So the definition needed to be modified.
In 1823, 2 guys simultaneously defined acids and bases in the exact same way. Bronsted and Lowry defined them. They didn't classify them by how they acted or what they tasted like or even what they were made of. They defined them. And this was an impressive feat because a huge class of molecules, to some extent or another, act as acids and bases. So to come up with a definition that fit all of them, that was not so simple. Bronsted and Lowry defined an acid as being anything that donates a proton and a base as being anything that accepts a proton. And when we say proton, what we're talking about here is a hydrogen atom without its electron. Usually this is happening in water. Acids and bases can react in a gas, but almost always they're in an aqueous solution. And when a proton gets donated in water, it is accepted by water. And H2O is converted into H3O+, the hydronium ion. So when an acid is added to water, it dissociates, like any other ionic compound, forming H3O+ and a negative ion. The acid has donated a proton to the water. Also a little chemistry terminology thing, we usually just write H+ or say protons in solution, when in fact we are referring to hydronium ions. It's just a shorthand. In reality, H+ in aqueous solution is always H3O+. Let's take a look at the dissociation of hydrochloric acid for some more terminology bits here. You see right off the bat that the HCl is donating a proton, but with many acids, particularly weaker acids, the reaction can actually go back the other way, with H3O+ donating its proton. So in this situation, every chemical in the reaction, also sometimes called the major species, can be called an acid or a base. On the left-hand side, the water is accepting the proton, so it's the base, and HCl is donating it, so it's the acid. And on the left-hand side, the Cl- would be accepting the proton, so that would be the conjugate base, and the hydronium ion is the conjugate acid. The phrase conjugate acid always used to confuse me because I thought it had something to do with with conjugating verbs, but it's actually the older original sense of the word, the one where conjugal or marriage-related visits for prisoners come from, which means joined together. For every acid, there is a conjugate base, and for every base, there is a conjugate acid. Previous definitions of acids and bases, particularly the one proposed by our old friend Arrhenius, relied on specific major species, most notably our friend the OH, or hydroxide ion. And while hydroxide is in most bases, it's not in all of them.
Okay, so this whole conjugate thing, we'll deal with it tomorrow. What is the Bronsted definition of acids and bases? Acid is anything that gives a proton, NH+, and a base is anything that takes a proton, or H+. This pretty much nailed down 98% of all acids and bases, as you will see. Here are 3 examples. You only choose 2. These are 3 examples of bases. Let me show you why they're bases. The best thing to do is imagine that an acid is somebody who throws a frisbee, the frisbee being the H+. So if you are the thrower of frisbee, then you are an H+. I mean, you're an acid. The frisbee is the H+. If you catch the frisbee, then you're a base. All right? NH3 is a base because it can catch a frisbee. So when it catches the frisbee, what does it become? Well, it doesn't affect the ends. How many H's do you have now? 4, and you were a charge of 0, and then you added a plus, so what is your new charge now? HCO3, this should be -1. HCO3 -1 plus H plus yields H2CO3, because the plus kills the negative, so that's a base. And PO4 -3 plus H plus forms HPO4, what's the charge? -2. So what happens when an acid meets a base? The acid gives the hydrogen plus to the base. Best thing you can do is imagine playing frisbee. Imagine playing frisbee. When you throw, you're the acid. When you catch it, you're the base. When you throw, you're the acid. When you catch it, you're the base.
For example, ammonia acts as a base when it reacts with hydrochloric acid to form ammonium chloride.
Did you see them playing frisbee? Who was the acid? Blue or teal? Blue. And who was the base? Teal.
There's no hydroxide, but there's definitely proton donation and acceptance going on. Now, acid.
All right. Hydrogen does not actually exist in water. I already told you this. It immediately joins with water to form hydronium, H3O positive. But for all intents and purposes, it is the same thing, and we will often use it synonymously. All right, let's stop right there.